Hi. Hi again. Busy Saturday morning. How are you? I hope you're good. This is going to be, this is a video I'm excited, I'm happy to make. It's net ionic equations. So there's a lot of information in here. We can talk about solubility. We can talk about weak electrolytes, non-electrolytes. I'm trying to figure out if I should put it all in one big video or just break it up into small videos. So I'm just going to start simple and then I'll make that decision. Okay. So I'm still in the process of making that decision right now. Where am I going to start? Where am I going to start? Okay. I'm going to start with solubility rules. Okay. Now, and I may end with solubility rules. I'll wait and see. So I'm going to write solubility rules. And you are not expected to memorize the basic solubility rules. If I can recall, and I've already told you this, what you need to know for AP, right, is that group 1, excluding hydrogen, group 1 ionic compounds. These are 4 ionic compounds. Okay. Do not include acids here. Group 1, soluble. Nitrates, soluble. Ammonium compounds. Remember, these are ionic, okay? Soluble, I'm giving you all the ones that are soluble. What else we say? We need to include acetates, soluble. This does not include acetic acid, okay? It's more molecular in nature. I think that'll do it. And when I get there, I'm pretty sure that will do it. Now there are many more solubility rules. So let's just look at them even I had my gifted kids look at them. So I'm going to have you look at them. And what you see are some similarities, right? Nitrates they're always soluble. Acetates, right? Acetates, soluble. Notice here's an exception that I didn't give you. Okay, moderately. That means it doesn't all the way dissolve. It just partially dissolves. Many of your halogens are soluble, with the exception of lead, silver over here, and mercury. You often see that, remember the silver nitrate and the sodium chloride making that AgCl solid, right? That's often present. But it's told to you, so you don't need to you don't worry about it too much. Sulfates are soluble except for bariums, leads, calciums, strontiums, okay? Carbonates and phosphates tend to be insoluble, right? They tend to be insoluble unless you have a group 1A or an ammonium with them. Now, something that I've noticed, people, no one's pointed it out to me. I've noticed it, it makes sense, is think about lattice structure and think about the steps to forming a solution, right? You've got to overcome solute. Well, these are our solutes. And notice that when that charge starts increasing on that anion, we see substances being insoluble, right? And I sometimes I've wondered, well, the larger the charge, the greater the attraction. So maybe the solvent attractions are not favorable enough to overcome the solute attractions. Thus, the substance is not soluble, right? I don't know. I made that up, but I wonder if it's true. Okay. Okay. So sulfides here, right? These tend to be insoluble as well, except for your group 1A, your ammoniums, and then there are some alkaline earth metals in there. You don't need to worry about that, all right? And then there's, we said group 1A and your ammoniums. So what we have to memorize are the ones that don't have a lot of exceptions to them, okay? All right, so you need to know that. Now, we've talked about dissociation equations, right? When an ionic compound dissociates into its ions. So I'm not going to go through that, but that definitely relates to this. And we know that we've got electrolytes, which are solutions that can conduct a current, right? So I'm actually going to move up here because I have a picture of that, right? So we can have strong electrolytes. Let's see if I can make that bigger so that you can see it, right? We can have strong electrolytes. We can have weak electrolytes, and we could have non-electrolytes. You should be able to represent all of these in a particulate level diagram or drawing, okay? And just as is provided for you here. So notice a strong electrolyte, we have 100% dissociation, right? Remember what makes, if I haven't, an electrolyte in this context is a solution that can conduct a current. And recall, it's the presence of those ions that allows the current to flow through it. So if we have 100% dissociation, then all of our solid has turned into ions. And the more ions, the more better, if that's a term, this solution can conduct the current. And everything here is ionized. So we have more ions and we have a better current being conducted. And you see here that we have a brighter light, right? That is referenced by the brighter light, right? So we have a better conductor, right? I don't want you to use that word. A better conductor simply means in your head what strong electrolyte means, right? You would use the scientific terms of strong electrolyte, and you just need to know that that means it is a better conductor. Thus, we have a brighter light, okay? And then, so you should be inferring, oops, I don't want a highlighter, I want a pen. You should now be inferring that here we have less than 100% dissociation, okay? So this would be totally soluble, whereas this would be slightly soluble. And we will get into that, and will be one of the later things that we look at. There's a lot of math you can do with this. We will not do that right now. Slightly soluble, that means less than 100%. Different compounds are soluble to different extents when they're slightly soluble. Some are more slightly soluble, some are less slightly soluble. There are numbers that we will learn to associate with that and to analyze that. Okay, so we don't have a brighter light. We have a weaker light, if you will, right? Not so bright, not so bright. That's what I mean by weaker. We have less ions, right? We've got less ions in solution. Where over here, everything turns into an ion. We have less ions in solution. And, we've got a weak electrolyte, we got a weak electrolyte. And then over here, and this could be slightly soluble, even insoluble substances, ionic, dissociate to some extent to produce ions. So notice these are going to be ionic in nature, okay? Where this one here, this non-electrolyte, we typically think of it as covalent in nature, okay? because covalent compounds do not contain ions. So when they dissolve, they do not dissociate into ions, right? No ions present. Right? Now, you need to understand that. So let's just draw it real quick, right? And this is just a same thing. What is a weak electrolyte? Dissociates partially, poor conductors, different extents of dissociation. We'll talk about these later. I don't. Strong electrolyte, complete dissociation, almost exclusively 100% ions, excellent, strong, good conductors. And then we'll talk about our acids and bases later. It's actually in this, we'll start talking about them in this unit, and then we'll get to equilibrium next semester. Okay. So just make sure that you yourself could draw the particulate level diagram of a 2.00 molar in a 2SO4 solution. We will make the sodiums red, and we will make the sulfates green. I could probably just do positive, negative. I'm going to assume I've got 1.00 liters, right? That means I've got actually 2 of these for every 1 of these. So let's say I've got 4 of these because I've got 2 moles. So that gives me 4 moles of sodium ions and 1 mole of sulfate ions. So I should have 4 sodiums for every 2 sulfates, right? So those are my positive ions, and those are my negative sulfates, and I have the proper ratio, and I have 100% dissociation. All right. Now, so this is my strong, and then I may have to put the water molecules in there, right? We've already talked about that. Next to my positive sodium, right, I would draw water kind of like a Mickey Mouse, and I would have the negative oxygen like that, right? And it's real simple. The only point is, do you understand that these are the attractions? And this is an ion dipole attraction here, okay? Oftentimes, AP will ask you to identify the type of attraction. In this case, we would have an ion dipole attraction. That's what's causing this, right? Step 1, separate your solute. Step 2, get those water molecules apart from each other, right? They've got that hydrogen bonding going on. Overcome those intermolecular forces here so that we have our 3 individual molecules. And then, right, so this is step 1. To overcome these forces is step 2. And then step 3 visually is putting those together, right? And you see how this step often releases energy, right? Often releases energy, okay? Whereas these steps require us to add energy, right? They require us to add energy. And sometimes this requires the input of energy too, but not very often, and we'll talk about that later. But this is step 1, step 2, and step 3 of that solution formation. I think that was a good time for me to go over that in more detail. Students have a hard time with that, so trying to make sure y'all don't. Okay, and now I would draw my weak electrolyte, right? I'm not going to worry here about mole ratios. I'm just going to show, right? Let's say that we have HF, right? So I would have HF HF, HF, and then maybe I'd have one H ion and one F ion. So we have incomplete dissociation, right? For every molecule, there's very few ions present, okay? And then your non-electrolyte would just have all molecules, okay? And if you remember, in the beginning, I said I'm not sure where I'm going to go. I'm going to stop this, and I'm going to call this solubility and electrolytes or something like that. But you're going to be assigned, I'm sure, to move on. Okay, but I'm going to just stop it to keep it short. And